Good. So yes, it's a great pleasure to welcome Professor Anna Watts, who's at the University of Amsterdam. And she originally is British, as many of you have probably gathered by now. Did her PhD at Southampton and has held an impressive series of fellowships over in the US at Goddard, at MPA, yes, MPA, and then Amsterdam before ultimately joining the faculty at Amsterdam. And Anna is a leading expert in neutron stars, and it's what she's going to tell us about today, specifically what this newish facility on the ISS NICER has been able to tell us about neutron stars. So I will hand over to you, Anna. Feel free to take it away.
Thank you. Well, it's very nice to be able to give this colloquium remotely. It would be much nicer to come over to the UK for a pre-Christmas shop-up, but unfortunately that's not possible at the moment. But what I'm going to talk to you about today is a NICER review of neutron stars. NICER being the Neutron Star Interior Composition Explorer, which is an X-ray telescope on the International Space Station. Hence the fact, can you guys see my cursor? Yeah, NICER sits on the International Space Station here. This is the mission badge here. You can see NICER itself. And what NICER is trying to do is to use X-ray emission from neutron stars to learn about the dense matter, the supernuclear density matter within the cores of neutron stars. Okay, so let me get myself into the right window. Okay, so let me start by telling you about the neutron star interior and why it's an interesting thing to study. So this is my kind of very rough schematic of what a neutron star looks like. It is a relatively small object, let's say a radius somewhere in the range 8 to 16 kilometers, containing 1 to 3 solar masses of material. And it has a layered structure. So we believe that neutron stars have a solid outer crust, which is essentially a nuclear lattice, dominated by electron degeneracy pressure in the outermost layers. And eventually, as you go deeper into the crust, the nuclei themselves become more neutron rich. And eventually, neutrons will start to drip out of nuclei. So that when we get towards the inner crust, we have a mix of the nuclear lattice, ionic lattice, degenerate electrons, and also free neutrons, which are most likely in a superfluid state. When we reach essentially nuclear densities, so that would be about 1 to 2 kilometers deep into the neutron star, then you can no longer sustain pure nuclei. The nuclei themselves dissolve at high densities to form some kind of nuclear fluid. And then our understanding of what is going on gets a lot more vague, and there are a lot of different theories. One possibility is that you have still predominantly neutrons in the core. However, they would not be 100% neutrons. You would have maybe 90–95% neutrons. You have to have some protons and electrons in there also for balance. But there are other more exotic possibilities. One is that you start to form stable states of strange matter, and the strange quarks may be locked up into baryons, so 3 quark particles with maybe 1 strange quark in there forming what we call hyperons, in addition to neutrons and protons. So you could maybe have 10% of hyperons in the deep core. The other possibility is that the baryons themselves actually dissolve and you end up with some kind of quark fluid. And again, most likely we think a mix of up and down and strange quarks. And some of these things may be in superfluid or superconducting states as well. So our theory colleagues have given us a whole host of possibilities when you're talking about densities getting up to perhaps 5 to 10 times nuclear density in the center of the star. So this is kind of the interesting, perhaps nuclear physics territory we want to explore. So let me put this into now a broader context, because what we're doing is in many ways complementary to what our physics colleagues are doing at accelerators and colliders like CERN. So what I'm showing here on this plot is a vastly simplified parameter space diagram of the whole universe, showing temperature on the y-axis and density or chemical potential, and I will use those kind of interchangeably on the x-axis. So basically, where we occupy the world around us, basically even in virtual space, basically is occupying this region down here of hadrons and nuclei. Okay, so essentially relatively low density, relatively low temperature regimes. What we would like to do is to understand what happens as we go to extremes of temperature or density. And so we'd like to understand if, for example, do all these things dissolve to form either deconfined quarks or a quark-gluon plasma? Now, essentially, we have a theory that in principle describes how the strong force behaves, basically quantum chromodynamics, but it is very hard to describe and compute these things from first principles because of the computational difficulties. So what we need to do instead, essentially, is to explore this with experiment and observation, and then compare those experiments and observation more likely to phenomenological models. So in terms of the parameter space that we explore, so for example, our colleagues who work in heavy ion collision experiments, basically at the various different colliders, are essentially working up in this high temperature regime primarily. Whereas with neutron stars, what we're exploring instead is the very high density, but much, much lower temperature regime, where by low temperature, I mean in comparison to the Fermi temperature. And for people thinking about neutron star mergers, perhaps in supernovae, they're going to a little bit higher temperature, essentially in here. So this forms part of a continuum, essentially, that we study with observation and experiment. So to give you an idea, essentially, of why neutron stars are so unique, as I said, potentially we can get up to 10 times normal nuclear density within neutron stars. We are forming material that is highly neutron rich, and much, much more neutron rich, essentially, than you will ever create in the laboratory. And that's because of the stable gravitational confinement, essentially in a neutron star, that lets us form these things. And the fact that, again, we have stable gravitational confinement gives us the chance to form stable states of strange matter, because it lets essentially weak interactions operate to create that. If you're making strange matter in a collider experiment, it's not stable, it's disappearing within fractions of a second, but in neutron stars, it may well be a stable state. So that is the type of nuclear physics, essentially, that we are able to explore, and how it is complementary to what is being done in the laboratory. Okay, so that is the nuclear physics motivation, essentially, for what we do. But we're astrophysicists, so we need to find something, essentially, we can measure with our telescopes to go back and connect this, essentially, towards the nuclear physics that we want to study. So essentially, everything runs around the kind of loop that I'm showing here on this slide. So I'm going to start down, basically, in the bottom left-hand panel, talking about core composition. And this comes down to the unknown microphysics. Basically, what are the particles that appear in the core of neutron stars? Is it just neutrons and protons and what we call nucleonic matter? Do we have hyperons forming, or do we have some kind of deconfined quark matter? And these are the unknowns in the composition and the forces between the particles. Now, those forces between the particles on the very smallest scale set what we call the equation of state. And this is a macroscopic relationship between pressure and density. You will note you can in principle put temperature on here as well. I'm going to mostly talk about cold neutron stars, so I'm going to ignore the temperature axis. I can come back to that in questions if people are interested. But essentially, all of our uncertainty about what goes into the core, the composition, and the microphysics goes into this pressure density relationship. What I'm showing here are just a range of the different models that we have that are viable at the moment. Some models are pure nucleonic, some have hyperons in, some have quark cores forming with nucleonic material around them, what we call hybrid stars. And this pale blue band represents a family of models that occupies a wide space, motivated by some nuclear physics theories. But these are the range of possibilities. So fine, we have a pressure density relationship. We then need to relate that to the structure of the star, and we do that using the stellar structure equations. Now, neutron stars have strong gravitational fields, they're relativistic objects, so we have to use the relativistic equations of stellar structure, the Tolman-Oppenheimer-Volkov equations, perhaps with rotation in there as well for the structure. And essentially, the equation of state is an ingredient in those stellar structure equations. Pick a central density, solve the stellar structure equations for an equation of state, and you will produce a mass-radius relationship. And that is what I'm showing in the top right-hand panel. So every one of these equations of state, essentially all this family of models here, gives you one particular mass-radius relationship. Okay, so in principle, there is a direct mapping across, and you can see the range that is occupied essentially by some of these current theories. That, radius is perhaps anywhere between 8 and 16 kilometers from, and I'm not showing all of the theories here by any means. Now, the mass and the radius and the spin of the star, and these are stars that can spin up to several hundred times a second, determine the exterior spacetime of the star. And now, finally, we have something we can perhaps get a handle on with observations. Because any radiation now that is coming perhaps from the surface of the star has to propagate towards us through this relativistic spacetime. And so essentially that radiation carries with it information about the mass and the radius and the spin in principle. So if we can use that radiation to tell us about the mass and the radius, we can then walk back to the equation of state through the stellar structure equations. And from there, in principle, we can walk back towards the nuclear physics and go back to our colleagues there and tell them what we found. So that is the loop of logic, basically, that we are following with many of our X-ray techniques, essentially to try and understand dense matter within neutron stars. Now, how well do we do before NICER came along? So essentially, we would like to be able to measure masses and radii of neutron stars. Radius is pretty challenging, but we have managed to do quite a lot just with masses alone. And that comes from our radio pulsar colleagues. So I have to give them credit for doing this. Basically, if you have a radio pulsar that is in a binary with another star, you can essentially time the binary very, very precisely. And you can use, for example, relativistic effects, particularly things like, for example, the Shapiro delay, if you happen to be looking exactly along essentially the orbital axis, essentially of the binary, and be able to see, as is shown in this diagram, the pulse is essentially changing as the neutron star essentially shifts around, basically within the binary, and see what is happening. In principle, you can also measure masses directly from this kind of radio pulsar binary timing. Our radio pulsar colleagues have been very, very successful in doing that for neutron star, and neutron star white dwarf binaries. And what I'm showing on this plot are the current tight mass measurements coming from neutron star binaries. Okay, so these are all radio pulsar measurements. I'm doing relativistic timing. There are a lot more measurements, but some of them, the error bars are much, much larger. So I'm just focusing here on the tight ones. This is a figure from Paulo Freire. And you can see they have a range of masses all the way up to the current record holder, which is about 2.1 solar mass. And I'm going to ask you just to keep an eye on those two, because I'm going to come back to these two sources later in the talk. But what does this mean essentially for the equation of state, basically for the dense matter physics? Well, if I go back to my mass radius diagram, basically what you can see is I need to be able to make neutron stars with a mass of at least 2.1 solar masses, because that's what we measure essentially with radio timing. So that means I can put a line across this plot and say, if my mass radius relationship does not get up to that line, forget it, I can throw it away. And hence I can throw away the associated equation of state model. So basically you can see all of the ones that I'm showing here meet this criterion. Before these latest discoveries were made, there were lots of equations of state down here as well, which got to lower masses, and we can now throw those away and say that they don't work. Okay, so there are models already that have been thrown away. What is much more difficult is measuring radius with radio timing. So what I'm going to talk about now, we're going to come on to talk about, is a technique for also measuring the radius simultaneously. So this is what NICER is trying to do. So let me just introduce you to NICER. This here, you're seeing the NICER instrument before the launch. It gives you a feel for how large it is. It's a slightly oversized washing machine size. This is one of my absolute favorite photographs of the telescope, because when my oldest daughter saw this, I think 2 or 3 years ago, I first put this in a talk. She was very briefly convinced that I was working with a bunch of ninjas, and very, very briefly, I was the coolest mother of all time, before she realized they were not ninjas, and it was all much, much less exciting. But it gives you a nice feel for the size of the telescope. NICER launched in 2017, basically towards the space station. It went up on a SpaceX Falcon 9 as part of a crew resupply mission. And then it was unpacked and installed onto the space station, which is why I have my Lego ISS behind me with a little NICER module attached. So basically, if you want to see, there's some lovely movies on the NICER website showing how NICER was unpacked and installed, vastly sped up. So if you have a little coffee break and some time, I can strongly advise you to go and have a look at that. Okay, so the nice thing about being on the space station is that people can actually go out and take movies of your telescope. So this, I hope you guys can see the movie, and it works over the internet. But this is NICER on the International Space Station, moving around, again, vastly, vastly sped up. You can see it's essentially swizzling around here. You can see the detector array basically coming in here, and you get a feel for the environment that we work in. So we have solar panels coming in and around, other things going on in the environment of the space station that control, set some limits on essentially where we can observe. I will also point out NICER, at parts of the design, it has to be robust to being kicked by an astronaut when they're out doing spacewalks. So that's something we have to worry about. Sometimes it has to be stowed and put out of the way because there is maintenance going on other instruments around them, or the astronauts are indeed out on a spacewalk. That can be a little bit frustrating when a very cool astrophysical transient goes off and we can't actually observe because someone is wandering around outside the space station. And that's something that actually happened very recently. It's incredibly annoying. But that gives you an idea of what NICER looks like and the environment. And that's quite different to most X-ray telescopes that are free flying, basically essentially where we don't have to worry about the space station environment. The advantage, of course, is that we leverage all the infrastructure of the space station for data transfer, power supplies, and so on. So that makes life a little bit easier in that regard. Okay, the technique that NICER is using is called pulse profile modeling. So what exactly is pulse profile modeling? So I've said we're trying to use radiation essentially from the surface of the neutron star and looking for relativistic imprints in that radiation. So we're dealing with particular classes of stars that have X-ray emitting hotspots on the surface. So the surface is not uniformly emitting in X-rays. Then essentially as the star rotates, we see this bright spot flip in and out of our field of view. What you're seeing here is a comparison between a kind of Newtonian gravity simulation and a relativistic gravity simulation. You can see, for example, that due to light bending, you're seeing both poles of the star. So it changes the radiation that we see, changes the spectrum, and it changes the overall brightness. And there's a whole host of relativistic effects which we understand and can model very, very well for neutron star spacetimes that set this observed profile, overall brightness in the spectrum of the radiation. So that is the technique essentially that NICER is using, is to model this kind of thing. The particular class of neutron stars to which we're applying this are rotation-powered millisecond X-ray pulsars. So these are non-accreting pulsars. The X-ray emission essentially is coming from charged particles in the pulsar magnetosphere, smacking into the surface and heating it up. And this is the simplest possible cartoon. Beautiful dipole model, essentially particles accelerating, smashing into the magnetic poles and giving rise to essentially bright X-ray radiation hotspots, essentially at the magnetic foot points. The dominant emission is in the soft X-ray band, and that is where NICER is looking. And it's about twice the peak effective area of XMM, just as a comparison. They are nice because they are extremely stable rotators, which lets us build up a lot of data over long periods of time, basically to do the technique that we want to use. Okay, so let me walk you through essentially the pulse profile modeling process. Because this is the whole analysis technique essentially that we've brought together. So first thing we need pulse profile data. So what is pulse profile data? We know the spin rate of these stars very, very well. And essentially we build up a phase resolved pulse profile, looking also at the spectrum of the radiation. So here is a very simple example. Every photon that arrives comes in at a certain rotational phase of the neutron star. We're talking stars rotating 100, 200 times a second. Because the special relativistic effects are strongest for us. The surface velocity of the star is coming to an appreciable fraction of the speed of light. And that also imprints information about the radius. Every time a photon comes in, we check its energy, we check the rotational phase it arrived at, and we drop it in a box. And we build up this kind of pulse profile, essentially with numbers of counts, basically in each box. So here you see something with 2 peaks per cycle, basically a faint one and then a brighter one. And that is the data that we are trying to model. We then need to have a model of the emission process. So basically I need to build a model of my star with a certain space-time. I need to decide how many hotspots I'm going to put on. One parameter in the model will be the angle that we're looking at the star from, how far away is it, what's the temperature of the hotspots that I'm dealing with, what size, what shape do they have. Then I need to perhaps have some atmospheric emission model. I need to have a good relativistic ray tracing model. And then for any choice of those model parameters, I can produce a simulated pulse profile. Then I'm going to do Bayesian inference in principle, basically to try and work out essentially the posterior distributions of all of those parameters in the model. So this model component here effectively is what I call my likelihood calculation, chance of getting the data given this choice of model and these model parameters. I also need to have a model of my instrument in there in order to make a proper comparison with the data. And then I need to run very, very large scale statistical sampling to run across my entire parameter space and to work out indeed the posterior distributions of all of these parameters. I also need to have priors on all of these parameters. So I might, for example, say, right, I'm pretty confident neutron star mass is somewhere between 1 and 3 solar masses. Maybe I have independent information about the mass of the star. I have some idea of what the inclination might be, or the distance perhaps for radio timing. So I can put those on essentially as priors into my model as well. So then we're doing large scale statistical sampling using supercomputers essentially to recover the parameters. So it sounds like a lot of parameters in the model, but it turns out we can recover well exactly what is going on. What we infer is not just the mass and the radius, but all the other parameters of the model as well. So the geometry, the hotspot locations, and so on and so forth. Okay, so let me now show you some real pulse profile data. These are 4 of the sources that we've been looking at with NICER. So basically here you're seeing, so slightly different color scale, but essentially overall numbers of counts, energy in keV against rotational pulse phase, and I'm showing 2 full rotational cycles for each of the pulsars. You can see that some are much better sampled in terms of total number of counts than others, and we build up data over time because they're super stable rotators, so we can take lots of separated observations and just build up these big data sets. And it takes us, the first data set we analysed was built up over a couple of years, essentially to get millions of photons to make these kind of profiles. This is in principle the best source that we could possibly hope to do. It is a pulsar for which we know the mass extremely well from radio timing because it's in a binary. It's 1.4 solar mass pulsar. The mass is known to about 3%. So in principle, isn't it super bright? We have loads of data on it. So that should have been the best one to start with. However, unfortunately, there is a bright AGN, curses of AGN, in the field of view as well. So this is the pulsar we have to view slightly off axis. And that means we had to have a very good understanding of the off-axis response of the NICER instrument, and that's taken us a little while to get a handle on. So in fact, we didn't start with that one. We started with this source, which has no independent information about the mass, but 2 beautiful peaks in the pulse profile. So this was the first source that we started to analyze, and the other 2 sources shown here are going to come later. So we've run into a number of kind of fun issues going through the analysis. One issue was the sun, and this is something that we hadn't realized would be a problem when we first did our data sets, but we were getting such bizarre results out of the analysis that we started to dig into a little bit. So it turns out the sun angle essentially varies towards the space station basically over time, and the optical photons can actually mimic X-ray photons in the detector. So what you see, for example, here is count rates per energy channel against channel for different sun angles. And if you include all of the sun angle data, you get this very, very strong peak down in the low energy channels. And gradually, as you make different sun cuts, you remove photons until hopefully you're only seeing the source. And so we quickly realized that we would have to actually drop some sun angles from our analysis in order to only be seeing stuff from the source itself rather than being contaminated by the sun. So this was news to me that the sun could be an issue for X-ray astronomy, but there you go, it is. So that's one thing we ran into. We then have to essentially test our simulation and inference codes. So there are 2 aspects that we had to essentially run through in a lot of detail. One was our relativistic ray tracing codes. We're dealing with rapidly rotating neutron star spacetimes to make sure that we're adequately modeling it. There's a very good theoretical understanding of how to do this, but of course, computational implementation is another thing. So we had several different groups in the collaboration with ray tracing codes, running tests on a bunch of example simulated problems to confirm that we were getting consistent results and that we understood what we were seeing. It uncovered a number of errors in previous codes, but that work was now done and we have codes agreeing to within 0.1%. We then have our sampling codes, essentially, that do the statistical inference, so that are computing, 10 to the 7, 10 to the 8 relativistic ray tracing calculations in order to do our statistical inference. This typically requires supercomputers, and we have 2 independent codes in the collaboration that can do this. My team's code in Amsterdam, which is available open source if anyone is interested, and we use the open source sampler multinest. And then there is an independent code from Cole Miller's team at the University of Maryland. So we also ran cross tests of our inference code, putting in synthetic data and verifying essentially that we could recover the input parameters to some reasonable degree of confidence. We then had to think about modeling the NICER instrument response, because that's a part of it, of converting, simulated, essentially data into real data for comparison to the actual data that we take. So this is something that we spent a lot of time over, of trying to work out how to deal with modeling the calibration uncertainty of the instruments. And there are energy independent calibration issues and energy dependent calibration issues. And what we tried to do was to build a model of that, basically within our group's code, to try and model to some degree the uncertainty. And we modeled some of it based on reference and calibration sources using work done by Renee Ludlam. And so we developed this model, which we put in, and we actually infer the instrument response also as part of our analysis. And this is something that we're now refining as well. So what you're seeing here essentially is our distribution of our prior distribution on the instrument effective area that we're assuming in our analysis. Then we also had to put in parts of our models of, okay, what kind of shapes are we allowing for these hot emitting magnetic pole regions? And when you go and chat to the pulsar theorists, they just kind of laugh because there is no, first principles model that tells you what pulsar emission essentially should look like. You get some kind of nice picture like this, perhaps from return current simulations, showing that perhaps you have circles, perhaps you have crescents of some kind. You might have multiple temperature components in there as well. And this is a very, very challenging thing to model. So essentially, we had to make some simplifications here because these are really computationally intensive simulations that we're doing. So what we eventually decided to do within the Amsterdam group and our simulations was that we would assume there were two emitting regions because there are two very clear peaks in the pulse profile for the first source we were doing. But we would take essentially parameterized models of the shapes and gradually make them more complex. For every increased degree of complexity, the previous model would be within that set, and we would gradually work up adding complexity to our polar cap models and see whether we could get something that looked like the data and examine things like the Bayesian evidence of the model to decide whether one was better or not. So our very simplest model that we took was to say, okay, let's assume we have two spherical emitting regions. And we allow them in principle to be anywhere on the star, but they're not allowed to overlap. They can have different temperatures, different sizes, and so on. And then we model and obtain the parameters for that. The next most complicated model, we had a concentric ring and a core for each polar cap. Then we allowed the center to move a little bit off center. We can allow this to be colder or hotter. That's one possibility. And again, two emitting regions overall. And you can see you can recover the simpler one simply by making these two regions the same temperature. And finally, we let the core kind of escape, basically an overlap, and this lets us create crescent shapes as well, perhaps by having this one cool and allowing this one essentially to be rather hotter. And we picked this because it was, astrophysically motivated by the simulations our pulsar colleagues were doing, but allows a wide range of possibilities. So we basically started working through this model sequence. And I'm going to show you, first of all, results for the simplest possible model, just two circular single temperature hotspots. We were able to very quickly show that putting them directly opposite each other, so allowing them to be antipodal, was an awful fit, just looked terrible. Huge residuals did not explain the data. So that one we could throw straight away. These things are not opposite to each other. So these are the results of the simplest possible model that we tried. Now, what I'm showing you here are posterior probability density plots, essentially for the main equation of state parameters. So that is the radius, the mass, and the compactness. So you're seeing 2D distributions here, and here are the one-dimensional distributions. This is for radius, and the dashed line essentially gives you our prior distribution. Here in the middle panel, you're seeing compactness, and then down in the lowest panel, you're seeing the mass. So you can see that the mass was kind of tending towards a very low value out of our prior range. The radius was coming around 10.4 kilometers, about 10% uncertainty. So, okay, so then we needed to look a little bit at model quality. Is this model a sufficient description of the data? So here is the data. This was kind of the best model to come out, and you can see it doesn't look too terrible, basically as the representation. And we can then look over all the residuals, are they distributed as we expect? Are there noticeable deviations? Is there structure appearing in here, essentially, which we would not expect if the model were a good fit? We can also get a posterior distribution on the instrument effective area and on the geometry parameters. And this essentially was the geometry that we were finding for these two single temperature hotspots. Looking at the star from one hemisphere, the two essentially emitting regions on the other hemisphere, basically one slightly larger than the other. So those are the results for our simplest model. And then essentially we progressed through this model sequence. We made one simplification quite early on, which is because these two peaks in the pulse profile are quite well separated, it's possible to say, one's associated with one emitting region and one is associated with the other. And it turns out that one of the peaks was very well fit by just a small circular hotspot. So what we did halfway through our runs essentially was just to freeze one of them and say, let's assume it's a small single temperature hotspot is good enough. to explain that particular peak, but we'll mess around with the structure essentially that we allow for the other hot emitting region. And this was important because I said these are extremely intensive runs, you know, hundreds of thousands of core hours on the supercomputer. So making this kind of simplification let us do it within our computational budget and seemed a reasonable thing to do given the results. What we then do is we do model comparison. We look at whether adding extra complexity is worthwhile. We looked at the evidence. We looked at the predicted background emission because we had some data from XNM for this source telling us what the expected background was going to be. So we were looking for consistency with that as well. We looked at the maximum likelihood and we looked at the residuals. And on the basis of all of those different comparisons, we identified a preferred model, which seemed to be our best description of the data. And that is the model that I'm showing you here. So this is our preferred configuration, what we called ST plus PST, single temperature plus protruding single temperature. It's a terrible term, but we're now stuck with it. Again, what you're seeing here are the dense matter parameters, radius, mass, and compactness. The compactness is extremely well constrained again, basically, and this was actually consistent across all the models that we tried. The radius is now coming in around 12.7 kilometers with about a 10% uncertainty, and the mass was coming in about 1.34 solar masses, again, with about a 10% uncertainty. So this seemed relatively reasonable. And the geometry that we had, very kind of similar in some respects to the previous one, looking at it from one hemisphere and the two emitting regions essentially in the other hemisphere, and absolutely not antipodal on other sides of the star. Again, we can do the same data model residual comparison. We can look at the inferred instrument effective area, which is shown here in red, compared to the prior in blue. You can look at essentially, you know, as we look at this from Earth, how is this generating the radiation that we see? Here we have essentially this small circular spot giving rise to the lower peaks in the pulse profile. This is now the bolometric pulse profile. And this arc here, essentially right on the limb, giving rise to the higher peaks that we see here. Now, I mentioned that there were two independent groups, basically with simulation and inference codes within the NICER collaboration. So totally independent codes working with independent methods. So Cole Miller's group ran their own independent analysis. And these are the configurations that they came up with and how they compared. So they had this is our two emitting region model, small spot and an arc, basically long extended arc. Cole's group came up with a very similar configuration. They allowed also the possibility of a third spot, and found this was very slightly preferred to have another kind of very low temperature spot here, but it was kind of marginal. These are the two main contributors. Again, a small spot similar to ours and a longer extended region, basically on the other side. Mass and radius a little bit different, but again, consistent basically within the error bars that we have on these things. So that gave us a great deal of confidence, essentially, that we're getting, you know, fairly consistent results out. So that was the first result that we published, December, I think last year, right at the end of 2019. So one thing I should probably say is first of all, how does this compare to other ways of measuring the mass and the radius? It's tough to measure the radius, basically, as well as the mass. I've already told you that. But one possibility that you can do is, again, an X-ray based technique. And you can look essentially at the overall spectrum of radiation without worrying about the rotation of the star, essentially just a phase averaged X-ray spectrum from either a neutron star that has perhaps been accreting, accretion has switched off and it's now cooling down gently, so it's in quiescence, or alternatively, a neutron star that's had a thermonuclear explosion. And you can use the thermonuclear explosion itself, a type 1 X-ray burst, model the emission from that, and again, extract information in principle about the mass and the radius. So this is something that has been done. It's possible to do it for a subset of bursting or quiescent neutron stars. You tend to need the distance in order to make this technique work, so that cuts down the number of stars for which you can do it. There are model-dependent aspects in there as well. For example, you need to think about what the atmosphere is doing to you. If the star is spinning, but you don't know the spin rate, but it's spinning very fast, that can modify essentially the effects on the spectrum. Perhaps if there is some small residual accretion going on, that would also affect the spectrum that you see. And there's been a huge amount of progress in the modeling of this that's been done over the last few years. What I'm showing here is just one example of inferred mass and radius, two different models for the same star, one allowing the composition, essentially the atmosphere, to be free and one fixing it. For essentially thermonuclear burst spectral modeling by Jonas Nattala and his collaborators, who are using really state-of-the-art burst atmosphere models. And the kind of numbers that they're coming up with are roughly consistent with the 12.7 kilometers, but again, also about 10% uncertainties. But at least nice to see some consistency from an independent technique. However, we're not just measuring neutron star dense matter parameters now from X-ray astronomy. Our gravitational wave colleagues are also doing this as well. So there was a lot of fanfare, of course, with the first discovery of the first binary neutron star merger in gravitational waves, GW 170817. And basically, due to the in-spiral of those neutron stars, you can try and measure the tidal deformability of the neutron stars as they spiral in towards each other. And that also depends on the dense matter equation of state. So the LIGO collaboration were able to measure mass and put limits on the tidal deformability, essentially from that in-spiral event. And as a result of that, they then also produced results for radius, okay? So what you're seeing here are two, again, posterior distribution plots for the two components published by the LIGO collaboration. So here you're seeing mass and radius against each other. This is the overall distribution of the radii, essentially of the two components, with the priors essentially shown in dashed lines and the posteriors basically up here. So somewhere between 12 to 13 kilometers, or sorry, 10 to 13 kilometers. A different model shown here, and this is a rather different prior on the radius. And this is because in order to translate mass and tidal deformability into a mass and a radius, you have to assume an equation of state model. So the radii numbers quoted by our gravitational wave colleagues are folding in information about the equation of state already. And that matters because you can see essentially the radii are pushing up higher here because the prior essentially is pushing you towards higher radii. So we need to think very carefully about the next step of our analysis. So we've taken pulse profile modeling, we've produced a mass and a radius. And if we want to translate that into dense matter things and we want to compare to our gravitational wave colleague results, we now need to think about the equation of state models that we're using. So I'm going to come on now to talk a little bit more about that. So choosing an equation of state model is a kind of fraught business. There are some first principles models that will give you parameters, pressure in terms of density, in terms of hyperon couplings and so on and so forth. But what people tend to use are families of parameterized models, purely phenomenological. And again, all you're trying to do is write down pressure as a function of density in here. So I'm showing a couple of examples that are very, very widely used in the literature. Again, this is pressure against density. And the first one here is called piecewise polytropic models. So what is done essentially is that at low densities, you're fitting to some kind of perhaps neutron star crust equation of state. In this particular model here, there is essentially a pretty decent model called chiral effective field theory, which can take you up to about nuclear density within some uncertainties. Beyond the nuclear density, they're kind of extrapolating. And what they're saying is we assume that in this region here, the pressure is some polytropic function, basically for some unknown constants and perhaps an unknown polytropic index, which will allow to range over a certain number of values. It then maps on at some transition density to another polytrope. And most people tend to pick 3 polytropes. You can pick 5 put together to span the space. But your model has essentially these 3 polytropic parameters and transition densities that essentially you then tend to try and fit when you're doing equation of state inference to figure out what the real equation of state is. This is done because these parameterized models that tend to be, you can fit most of the kind of better motivated physical models with a piecewise polytrope if you try hard enough. Now there is one disadvantage with this, which is your speed of sound has discontinuities if you do this by joining the polytropes together. So a second class of models that's now quite popular is to write down your equation of state in terms of the speed of sound, some kind of equation. We have some physical ideas about what the speed of sound should be doing in dense matter and some limits. So you can write down, for example, this kind of model with a few open constants, A1, A2, A3, shown in here for parameterizing the speed of sound. And then you obtain your pressure relation essentially by integrating that. So these are the kind of models that we're working with. Take the mass and radius we've got from pulse profile modeling, and then do the second stage of inference through an equation of state model to get the pressure density relation. We have to decide ranges for the free parameters and put priors on those. Okay, so that is a next and important step. And what a lot of people do is that they will say, okay, I want my equation of state to span a certain range of space. So I'm going to pick parameters within bounds. And they will perhaps pick something that sounds conservative, like a uniform prior on all the parameters within bounds. However, if you pop back here, these equations of state are sums of terms. And if I'm picking uniform distributions on all of these different parameters, and I'm summing a lot of them together, I'm essentially running into something close to the central limit theorem, is that I end up with something that's peaked. It's getting close to Gaussian, just as a result of making what I thought were fairly conservative choices on parameters. And so what you're seeing here for piecewise polyneuropes, this is the prior density, essentially on the central pressure and density shown here. And what you can see is that for piecewise polyneuropes, it ends up being quite peaked basically over here. So I'm automatically pushing, just by my choice of priors on my equation of state parameters, I'm automatically preferring a certain part of pressure density space. Absolutely no physical motivation for this whatsoever. It's just the way that I have mathematically chosen to parameterize my space. Speed of sound gives you something slightly different. Basically, you're pushed down in a slightly different direction. Okay, so then when you translate this into a mass radius relation, which is ultimately what we also want, so rather a full function rather than just individual values, what it means is that effectively my equation of state choices say I automatically prefer, for piecewise polyneuropes, before I've even started, radii between 12 and 13 kilometers. For the speed of sound model, I prefer 12 kilometers, but then with this kind of heron shape, duck face, essentially coming in at the top here. And that is because of my choice of parameterization. And you can see essentially that the range of preferred mass and radius is way narrower than what I assumed when I did the pulse profile modeling. So when I did my NICER analysis, I've allowed the possibility of any mass, essentially between 1 and 3 solar masses, and I've allowed radii, from 8 kilometers up to 16. This is way, way narrower. So I need to be aware of what I'm doing when I do my equation of state inference. So let me now show you one example of how that works. So this is an analysis where we started off working with colleagues in Darmstadt with, again, one of these parameterizations, piecewise polyneuropes, and we took speed of sound as well. We started off looking at the full range of kind of prior space. We popped in, first of all, the constraint from our radio pulsar colleagues, that we know we have to be able to make radio pulsars about 2.1 solar masses. So we put that in, first of all, as a cut. So what that does is it takes you from this kind of solid black line in the left panel towards these dashed and dotted lines. This is the 68% region, and this is the 90% region essentially shown here. So basically that high mass radio pulsar constraint cuts out a lot of this low mass parameter space, which I'd mentioned to start with, okay, because you have to be able to get up here. We then put in the GW 1708-17 results for tidal deformability using our equation of state model to make sure everything was consistent. What that does is it then pushes you slightly down, basically towards lower radii. So it moves you towards these green regions shown here on the right, because the GW 1708-17 results favor slightly softer equations of state. Then we popped the NICER result in. Now, a NICER result is not terribly constraining yet, it's 10% errors, but what it does is it shifts you slightly back, essentially towards higher radii. So this is kind of where we are, and a lot of people have done similar analyses with different equation of state models. And I think what I can say about our results, and I can also say about everyone else's right now, we are still prior dominated. Because of the choices we're all making in how we parameterize equations of state, we're not learning much over the prior. It happens by pure fluke that the peak of the prior is around about 12 to 13 kilometers, and that's where our NICER result sits. But our NICER results and also the gravitational results don't kind of narrow us in. We're not really controlled by the data so far. One thing that is interesting to note again is our particular choice of equation of state parameterization doesn't have a lot of prior space up towards these kind of high radii. We now have this other gravitational wave event, GW 1908-14, which has a 2.6 solar mass object in it. And there is a lot of debate as to whether that is a neutron star or a black hole. So there is some question now of, well, should we be allowing some prior space up here to see if we can make a 2.6 solar mass object? And that is something we're now looking at, of whether we need to try a broader range of equation of state parameterizations, because it's just not even included in our prior in the model that we tried so far within our group. Other groups have tried slightly broader ranges, and I think we probably should as well. So this is where we stand, I think, for essentially the dense matter constraints. So let me now move tack a bit and talk a little bit about the astrophysics constraints in my last few minutes, and talk about the implications for magnetic fields. We had this lovely cartoon picture of a beautiful dipole field millisecond pulsar, which we started out with. And essentially, we've come up with this geometry where the hot emitting regions are in the same hemisphere. They're weird shapes. Okay, 5 minutes, that's good. And so we now have to think about how to explain this. So you can't do this with the dipole field. In order to do this, you need something much, much messier. Something like what's called a quadradipole magnetic field instead. I'm told these things are stable and it's possible to create them. But we now need to think about how do you make this in terms of stellar evolution. These rotation-powered pulsars have been spun up through accretion, we think. So where did this weird magnetic field structure come from? Was it there during the accreting phase, for example? Did it come from the supernova? Did it get built by accretion? You know, is this reasonable, or is there something wrong in the way that we parameterize and model things in our analysis? You can also think about the multi-wavelength emission from this pulsar. The pulsar that we looked at emits in X-rays, but it also emits in gamma rays and radio. So here you're seeing the 3 different wave bands and the pulse phase. Most of the radio and gamma ray analysis to date has assumed a perfect dipole, and it's not a dipole near the surface. So we need to work out whether we can consistently explain emission in all 3 wave bands. There have been some very nice simulations recently by Alexander Chen and collaborators at Princeton trying to do this and taking our field structures and seeing if they can recreate the 3 waveband emission. It seems like it might be possible, which is rather nice. At some point, they may come back and tell us it's not possible, and then we'll have to modify our analysis. Most important thing is that we have broken the mission badge, which I'm extremely proud of. My first mission that has a badge, we've ended up with it looking like this. If we've broken the lovely pulsar on the front. So my postdoc, Andy Balouse, made this, and I'm rather proud of it. So what happens next for NICER? Basically, we got through the last senior review, and it's scheduled to run to the end of 2022. I guess we all hope it will be able to run for a little bit longer because it's producing some beautiful stuff for neutron stars and for black holes as well. We are refining our analysis technique. We're improving our model of the instruments, of the atmospheres. We're working out how to include background information from XMM directly into our inference pipelines to get better handle on that. So there's a lot of work being done there. We have 4 new sources that we're working on for analysis, and this includes 2 known high mass pulsars. So in the bottom left, you see the constraints, again, 68% and 90% credible regions that we have for the pulsar we've done, so very broad, and some equations of state. We have this very, 1.4 solar mass, but very well-known mass pulsar. Strong prior on the mass probably means a tight posterior on the radius. We have this high mass pulsar that will be the next one we release, I think. So this is kind of cool. So we'll put a nice radius on this one. We also need to think about what does it mean for neutron star evolution to have these kind of patterns. Do we need to modify our models or our prior space that we analyze in terms of surface patterns? And then we're also thinking ahead to the next generation. The sources that NICER is looking at rotate up to a couple of 100 times a second. If you can get up to 600 Hertz, you have a lot more kind of special relativistic effects. And in principle, that would help you to constrain the radius better. The constraint should scale basically with the spin frequency of the star. That means you need to go to accreting neutron stars. And we're lucky that accreting neutron stars have essentially spots on the surface as well. And the next generation of telescopes, essentially that we are looking to launch, are going to have larger effective area to enable us to get at these accreting neutron stars. We'll also potentially have X-ray polarimetry that starts to constrain the geometries as well. One possibility for that is the enhanced X-ray timing and polarimetry mission. This would be a joint Chinese-European mission, again, upping the effective area to several square meters, again, so much, much larger than NICER, also going to harder X-rays, which lets us get at the accreting stars and having a polarimeter as well. If that goes ahead, that will be launched in 2027 is the current date. Another possibility is StrobeX, which is a NASA probe concept. Again, kind of mega NICER plus a large hard X-ray detector, several square meters to let us get at these accreting neutron star sources. And then we also need to think about the modeling of these accreting sources as well. The astrophysics and the emission models for the hotspots are different, the atmospheres are different, and so we need physics motivated emission models to model these, not only for bursting sources that have hotspots, but also for accreting pulsars. We need to think about where the radiation comes from, how do we parameterize that in our analysis. And we also need to deal with the fact they're not so stable, they tend to vary, so we're going to have to work out how to put that into our pipelines as well. So there's some fun analysis challenges to happen there. So let me stop essentially and wrap up. NICER basically has shown that pulse profile modeling works. We've got first results at the 10% level for mass and radius, and those will be tighter with the next sources that we report. The analysis has thrown up a lot of challenges, basically on the data, on the instrument, on the modeling, and the astrophysics really matters. So how you put in these surface patterns is important, but the nice thing is it gives you not only the mass and radius, but also all this information about the geometry of the system as well. But I think we need to basically get more results and tighter results before we can really start making inroads in constraining dense matter, and that may take us into the next generation of telescopes. So I will stop there and take any questions, and I hope I haven't overrun too much.
Oh, fantastic. Thanks so much, Anna. You obviously can't hear the cheers and raucous applause that are going on in various households around the country, but and internationally even, but it's happening, it's happening. Right, cool. Let me stop the recording and we'll move on to the Q&A session.